Hello dear students, welcome back to your physics class. On today's lesson we are going to solve the questions that related with the conservation of angular momentum. If you remember, in a previous lesson we talked about the conservation of angular momentum and the angular momentum. The angular momentum is the product of the object's moment of inertia and it is angular speed and measured in kilogram meters square per second. And on today's lesson, as I told you, we are going to solve all questions that related with the conservation of angular momentum. For non-rigid body, such as the ice skater, when the net torque acting on the ice skater is zero, in that case, the angular momentum is conserved. So the ice skater can change its angular speed, so it can increase its angular speed and decrease its angular speed by extend and close the hands and feet toward itself or away from his body. In that case, the angular speed changes and also the moment of inertia changes. But for the rigid body, such as the bicycle tire, the ceiling fan, or the object that during rotating its shape doesn't change, its mass doesn't change, in that case, the angular momentum does not change when the angular speed increase or decrease. But for the ice skater, when the net torque acting on the ice skater is zero, in that case, the angular momentum is conserved, even its angular speed increase, but its angular momentum does not change, because when the angular speed increases, the moment of inertia decreases, so in that case, the angular momentum will be conserved. So before solving the questions, we have some tips and some notes. Rotating objects have angular momentum which is conserved in the absence of the external torque. For rigid body or geometric objects such as ring, D6 cylinder, pulley, or merry-go, in that case, the moment of inertia of initial moment of inertia is equal to final moment of inertia. Okay, why? Because the radius of the rigid body such as ring, D6 cylinder, or something like that, its radius does not change. For example, let's say when a merry-go rotating, okay, during this rotating, the radius of the merry-go does not change, okay, but the object on the merry-go changes, such as a student, a piece of putty, or something like that, okay. Any object placed on the rotating object, the moment of inertia of a said object is considered as a point mass. Therefore, final moment of inertia of the object is equal to mr square. Initial moment of inertia of the object is equal to 0. When does? If the object placed, when the question says the object placed onto the merry-go or geometric shape, for the placed object onto the geometric shape, in that case, initial moment of inertia is equal to 0 because the object does not rotating. When, for example, this is, assume that this is a merry-go, okay? So this merry-go is rotating, for example, okay? So if you place a piece of putty or an object into the merry-go, in that case, at first, the object has no moment of inertia. Its moment of inertia is 0. Why? Because its radius is 0. The object is not rotating or does not moving on a circular path, okay? Because in the moment of inertia, we need what? Mass and distance from the axis of rotation. Do we have the distance from axis of rotation? No. So that is why in that case, when the question says place it, an object, a piece of putty, or any object is placed into the geometric shape such as a solid cylinder or merry-go, in that case, the initial moment inertia is equal to 0. After the object placed on the geometric shape, okay, in that case, this object considered to be a circular motion, considered to be a point mass, this object becomes what? Point mass. Okay? Why? Because the object is entangled or fixed at the surface of the merry-go, and the merry-go is rotating. The object's angular speed has the same angular speed of the merry-go, and the object is moving in a circular path. For every circular path, the object considered to be a point mass. So the moment of inertia of point mass is always equal to mr square. Is equal to what? mr square. if the object is placed at the edge of the geometric shape, also this is very important, be careful. When the object is located at the edge of the geometric shape, okay, so assume that the radius of this geometric shape is 2 centimeters, for example. If the object start moving at the edge of this merry-go, for example, when a child is moving at the edge, okay, so R initial of the object is equal to the radius of the geometric shape or merry-go. Okay, so the initial R for this child is also equal to 2 centimeters. Why? Because the object located at the edge. When the object, in the case when the object is located at the edge of the merry-go, in that case, the radius of the object or the student or the child is equal to the radius of the geometric shape. R initial of the object is equal to R initial of geometric shape. If the moment of inertia is not given, so therefore you have to find it like for ring, pin hook, or bicycle tire. I is equal to mr square. For the D6 cylinder is equal to 1 over 2 mr square. An object's moment of inertia increases and its angular velocity decreases with increasing distance from axis of rotation, and vice versa is true. When the moment of inertia increase, what happened to the angular speed? Decrease. Okay? Is it possible for ice skater or skater to increase his angular speed? Increase angular speed without, I think, any external torque, yes, of course. How? By decreasing moment of inertia. But in that case, angular momentum is conserved. Is it possible for the ice skater to increase his angular speed without any external torque? Yes, of course. By in the case when he brings or she brings her hands or his hands and feet toward her body or his body. In that case, the radius decreases, moment of inertia decreases, but angular speed increases. Okay? Sample problem 2D. Look at this sample problem. A 65 kilogram student is spinning on a merry-go-round. Okay? That has a mass. What is this? This is mass of what? Or the mass of the merry-go. So we have two shapes. We have two, in that case, we have two objects, student and the geometric shape. Our geometric shape in this question is what? Merry-go. Okay? So it is very important to write down all the given value for each system, like student and the geometric shape. The mass of student was given 65 kilogram. Mass of merry-go was given 5.25 times 10 power 2 is equal to 525 kilogram. The radius of the merry-go is 2 meters. So this radius is R initial and R final. Why? Because merry-go is a rigid body. So that is why for every rigid body and for every geometric shape such as a pulley, merry-go, D6, solid cylinder, bicycle tire, in that case, R initial always equal to R final. It means that initial moment of inertia is equal to final moment of inertia for the geometric shape. Okay? R initial 2 meter and also R final is 2 meter. R initial is equal to R final for geometric shape. Okay? She walks from the edge. What do you mean by edge? It means that the student is start moving from the edge. It means that R initial is 2 meter. Why? The question does not mention the radius or the distance of the student from the axis of rotation at first. But the question mentioned another thing. The question says she walks from where? Edge. From edge, this point is the edge of the merry-go. So it means that R initial for the student is equal to 2 meter. Why? Because from the edge of the merry-go toward the center. Okay, if the object is moving from the edge from the edge of the merry-go toward the center, in that case, what happened to the radius? Decrease. When the radius decrease, what happened to the moment of inertia? Also decrease. What about the angular speed? Must be increased. Okay. If the angular speed of the merry-go-round is initially 0.2 rad per second, omega initial 0.2 radian per second, As I told you, the angular speed must be increased. So in that case, omega final must be bigger than, omega initial. Look at the final answer. The final answer, omega final, yes, absolutely is bigger than the initial angular speed. Why? Because the student walked from the edge of the merry-go toward the center of the merry-go. In that case, she decreased her distance from axis of rotation, so the angular speed must be increased. Okay? What is the angular speed when the student reaches at this point? This is R final. The student reached at which point? At this point. R final is equal to 0.5 meter. How can you solve this question? It's very important to write down the equation at first. L initial is equal to L final. We have two objects in this system, student and the geometric shape, merry-go. So that is why the equation becomes like that. I initial for the student plus I initial of merry-go times it is angular speed is equal to I final for the student plus I final of merry-go times omega final. So this omega initial is the same for both the student and the merry-go at this point. Look, when the student is here at the edge of the merry-go, what is the value of the angular speed of the merry-go? The value of the angular speed of the merry-go is 0.2 radian per second. Because the student is on the rigid, on the merry-go, so in that case, every point, look, every point on the rotating object, they have the same angular speed. Okay? So the angular speed of the student is also is to 0.2 radian per second. When the student reaches near the axis of rotation, in that case, omega final for the merry-go is equal to omega final for the student. Okay, so that is why we have to write down the omega initial outside of the bracket. Okay, so what is unknown? Omega final is unknown. So you can rearrange this equation, omega final. What is with omega final? We have this two quantity, I final for the student plus I final for the merry-go. Here what we have, I initial of the student plus I initial, this is initial, merry-go times omega initial. Okay, do we have omega initial? Yes, was given, but we don't have I initial and I final for the students. I initial and final for the students. Okay, for the student, I initial is equal to what? Because the student considered it to be a point mass. Okay, it becomes a point mass. For the point mass, moment of inertia is always equal to m r initial square. Mass 65 for the student times the initial distance of the student from the axis of rotation was given, because the question says she walks from the edge, so that is why R initial is equal to 2 square. Okay, so is equal to 260 kilogram meter square. This is initial angular speed. This is initial moment of inertia for the student. Okay, write down here 260. I final for the student, because she walks from the edge to the near axis of rotation, the radius and the distance from axis of rotation must be decreased. R final square 65 times R final 0.5 square is equal to what? 16.25 kilogram, 16.25 kilogram meter square. This is the final moment of inertia for the student. Okay, this is 16.25. So what's remain? The moment of inertia for the geometric shape. For the geometric shape, be careful. The moment of inertia, initial moment of inertia is equal to final moment of inertia because our shape is merry-go. So the merry-go's moment of inertia is equal to 1 over 2 mr squared. 1 over 2 times 525, the mass of the merry-go, times it is radius is 2 squared, which is equal to I initial is equal to I final for the geometric shape and is equal to 1015 kilogram meter square. This is 1015, this is 1015. And also we have initial angular speed 0.2. Now we have all the all quantities, so that is why you can find final angular speed. Okay? Look, after replacing into this equation, omega final is equal to what? 0.246 radian per second. So in that case, as the student approaches the center of the merry-go, its moment of inertia decreases and its angular speed increases and angular momentum remain constant. Okay? Look at question 1 in practice 2D. A bicycle wheel. What is our geometric shape? Bicycle wheel. Its moment of inertia is equal to what? R squared. R initial is equal to R final because bicycle wheel is a rigid body. Okay? What is the mass of the ring of bicycle wheel? 2 kilograms. With the radius. This radius is initial and final. R initial, R final is equal to what? 0.3 meter. There's at a constant angular speed with 25 radian per second. Omega initial for the bicycle is equal to what? 25 radian per second. Okay? This is the bicycle ring. Okay? It's rotating with the 25 radian per second. Okay? When 0.3 kilogram reflector is at a distance 0.19 meter. Okay, when the reflector is, this is reflector. What is this? This is reflector. It is distance 0.19. This is R initial. R initial, sorry, its mass is 0.3 kilogram. At which point 0.19 meter from the axis of rotation. R initial is equal to what? 0.19. Okay, the reflector is at 0.19 meter from the axis of rotation. What is the angular speed of the wheel when the reflector slides to a distance 0.25? To what? To 0.25. So in that case, sorry. The reflector is at a distance R initial here. Okay, this is R initial. 0.19 to where? To 0.25. Okay, what happened to the radius? R increase or decrease? R increase. So moment of inertia also increase. But its angular speed must be what? Must be decrease. Okay, so to find the angular, so in that case, omega final must be less than omega initial. Without solving, you can know which angular speed is bigger. Look, final angular speed is less than the initial angular speed, which was 25 radian per second. Okay, what is the angular speed of the wheel when the reflector is slides to distance 0.25? R final 0.25 meter. Okay. How can you determine the final angular speed? As I told you, at first you have to write down L initial is equal to L final. Okay. Initial angular momentum, because we have two objects. Initial moment of inertia for the reflector plus initial moment of inertia for the ring times initial angular speed is equal to final moment of inertia for the reflector plus final moment of inertia for the ring times omega final. What is unknown? Omega final is unknown. Omega final is equal to what? I final reflector plus I initial ring, which is the geometric shape, and I initial reflector plus I initial of ring times omega initial. So now we have to find the moment of inertia for the reflector and for the ring. As you know, for the reflector, for what? For reflector. At first, the reflector at a distance of 0.19 meter from the axle. Okay, so that is why initial moment of inertia for the reflector is equal to what? Because the reflector must be considered is a point mass. The reflector is a point mass, so that is why is equal to mr initial square 2 times mass of mass of the reflector. Mass of reflector is equal to what? 0.3 times 0.19 square is equal to 0.01 kilogram meter square. This is initial moment of inertia for the reflector. Okay? Final moment of inertia for reflector is equal to mr final square. The mass of the ring, geometric shape, 2 kilogram was given. Time is, it is radius 0.3 meter square. Okay, so in that case you can calculate by your calculator. So you can get this number 0.018 kilogram meter square. What is this? This is the final moment of inertia for the reflector. For the geometric shape, for the ring, as I told you, I initial is equal to I final. So I initial is equal to I final is equal to mr square. Mass was given 2 kilogram. Okay? Sorry, this is final. Moment of inertia is also 0.3. This is not 2. Be careful. Okay. This is 0.3 because the mass does not change when the reflector slides to 2.5 meter from the axis of rotation. But the mass of the ring is 2 kilograms. Sorry, I apologize about that. 2 times r is constant, 0.3 square. The moment of inertia for the geometric shape is equal to 0.18 kilogram meter square. So you can substitute into this equation. This is 0.18. This is 0.18. But initial moment of inertia for the ring is 0.01. This is 0.018. You have to add up these two numbers, then multiply by the initial angular speed, which was 25, and add up the denominator. So you can find the final angular speed, which is equal to 24 rad per second. In that case, because as the object moves away from the axis, a bicycle tire, so it is moment of inertia increase, and angular speed must be decreased, but it is angular momentum is remain constant. Okay. Question 2, practice 2D. A solid vertical cylinder. Very good question, guys. Listen carefully, please. A solid vertical. What is our shape, our geometric shape? Cylinder. The geometric shape in this question is what? Cylinder. The moment of inertia for the cylinder is equal to 1/2 mr square. Mass of cylinder is given 10 kilogram. Its radius is 1 meter. Okay, this is cylinder. Okay, this is the axis of rotation of the cylinder. When this cylinder is rotating with the angular speed of 7 radian per second. Okay, so the distance from the axis of rotation to the edge of the cylinder is given r is equal to what? Is equal to 1 meter. Okay, so the radius of the cylinder is 1 meter. Okay, and its mass is 10 kilogram. Rotated with angular speed 7 rad per second about fixed vertical axis through its center. 0.25 kilogram piece of putty is dropped. So in that case, the piece of putty is dropped at to where? A piece of putty is dropped. This is a piece of putty is dropped. In the case of dropping object to the cylinder, to the geometric shape, in that case, R initial is equal to 0. R initial of the putty is 0. Why? Because the object is not on the rotated body such as cylinder or merry-go. The object is outside of the cylinder, so that is why it has no distance from the axis of rotation. Okay, so that is why I initial of this object is also equal to 0. But when dropped into on 0.3 vertically at a point, drop it vertically at which point? 0.9 meter. 0.9 meter from where? From the axis of rotation. And also you can say drop it at a point 0.1 from the edge. But 0.9 from this axis of rotation. Both of them are correct. If the question says if the putty is dropped at a point 0.1 from the edge, so it means that it is distance from the axis of rotation is equal to 0.9 meter. Why? Because already we have the radius of the cylinder, 1 meter, 1 times 0.1 is equal to 0.9 meter, because we need the distance from the axis of rotation. When we say the moment of inertia of the putty is equal to mr square, what do you mean by this r? This r is the distance of the object from the axis of rotation, not from the edge of the object. Okay, so final radius is equal to what? Final distance from axis of rotation, 0.9 meter for the putty. Final distance is equal to 0.9. Omega initial for the putty is also equal to 0. It has no omega angular speed, but the cylinder has angular speed. Look, from 0 to 0.9, what happened to the distance from axis of rotation? Increase or decrease? Increase. From 0 to 0.9. When r increase, what happened to the moment of inertia? Also increase. When the moment of inertia increase, what happened to the angular speed? Must be decreased. So this final angular speed, when we now we try to find it, it must be less than 7. The final angular speed in this question must be less than 7. Why? Because the angular momentum is conserved, and final angular speed is absolutely is less than 7, is equal to 6.72. How did you know the final angular speed must be less than 7? Because you have to say, because the distance from the axis of rotation increases from 0 to 0.9, moment of inertia increase, but angular speed must be decreased. Okay, now write down the equation of the conservation of angular momentum. Okay, I initial for the putty plus I initial for cylinder times omega initial, which was 7, I final for putty plus I final for the cylinder times omega final. What is unknown? This omega final is unknown. I final for putty plus I final for the cylinder, I initial for the piece of putty plus I initial for the cylinder times omega initial. Okay, now for putty at first, I initial is equal to 0. Why? Because the piece of putty is dropped. So I final for putty is equal to what? Because the putty is considered to be a point mass, mr final square. Mass of putty was given 0.25 times r final, 0.9 square is equal to 0.9 25 kilogram meter square. I initial 0, I final 0.2025. So the moment of inertia for the solid cylinder I initial is equal to I final, and moment of inertia for solid cylinder is equal to 1 over 2 mr square. We don't have initial and final because the radius and the distance from axis of rotation does not change for the cylinder. 1 over 2 times mass of cylinder 10 kilogram. It is radius is 1 meter square, okay, which is equal to what? 5 kilogram meter square. 5, and we have 7 radian per second here. Okay, by calculator you can add up and finding the value of final angular speed for the cylinder, which is equal to 6.72. R increase, I increase, omega decrease, L is constant. Okay, so we finished it, the angular momentum, and we solved it. All questions that related with the conservation of angular momentum and the angular momentum. In the next lesson, inshallah, we are continuing to explaining the section 3 in chapter 2 about the rotational kinetic energy. Thank you for listening. Keep up your best doing. See you again, inshallah.